All right, hello guys. We're going to talk about some exponential functions some more today, and it's about to get real exciting. So hold your horses. We're going to talk about some cool stuff today. All right, so we're going to just add to that section of notes that we started yesterday. Don't write down this first example, but I pulled this off of the end of course exam from last year or the year before, I don't know, one of the end of course exams. And you know how to answer this. So let's look at it. It says the population of snails in a tank at the aquarium is found to triple every year. All right, so we've got population tripling every year. So you know you're going to be doing something exponential. Mark visits the aquarium and counts 80 snails in the tank. Oh, hey, that's our initial amount. That's what we're starting with, 80 snails. Write a function, okay, f of n, that's weird, that's not an x, it's an n, to model the number of snails in the tank n years after Mark's visit. Okay, so what do you think we're going to do differently with this n? Well, we're just going to put n's wherever we would normally have x's, so that's not a huge thing. But do you remember how the formula works? All right, so we need to start out with our initial population, so 80 goes here. Now we're going to do times. All right, if it's tripling, we put a 3 here. And then it's going to be to the power of not x, but n this time. There we go. Okay, so this would be the answer to this question. It didn't even ask you to do anything else after that, which is a lot kinder than I've been to you guys. This question was also on a recent end of course exam, so it's very similar. A scientist is studying wildlife. She estimates the population. Anytime they tell you a population, unless they say like it's not exponential, it's going to be exponential. The population of her bats is 270,000, okay? She predicts the population to grow at an average rate of 2.9%. Oh, well, that's different. That doesn't just say like, oh, it's doubling or it's tripling. That's like a weird in-between number. And in fact, you're going to be tempted to make it like 270,000 times 2.9 to the power of x, but that is not right because that's almost tripling, right? 2.9 is almost the same thing as having a 3 here. But it is not almost tripling every time. It's only going up by a little percent every time. So this is not right. That's not at all what we want to do. So what we're going to talk about is how to format these equations if they give us a percent that it increases by every year. So here's our formula right here. It's almost the same thing, but there's a minor difference. We still have our A as our initial amount. We still have times, but instead of B here, which was just 2 or 3 or 4 if it was quadrupling, we have something that looks a little bit different. It's 1 plus r, where r is whatever the percent is. So go ahead and write this down. Pause the video if you need to. And notice it's still to the power of x. So let's practice using this function here. So example 1, the number of subscribers to National Geographic increases by, actually, I meant to change that. This is Sports Illustrated. Those are the actual numbers for Sports Illustrated. So since I took the time to look it up, I'm going to take the time to fix it. Okay. Increases by 15% every year. Currently, there are 2,750,000 subscribers. And believe it or not, that number is smaller than National Geographic's, which is why I picked it, because I wanted it to be a little easier on you guys. Anyway, we need to write a function to model the number of subscribers after t years. Okay, so what was that function again? It looked like this. F of x equals, all right, so f of x equals, now we need our initial amount. A is the initial amount. Well, we're going to start at this 2,750,000. Okay, let's keep going. Times, now here's the weird thing, we have 1 plus whatever our percent is, but there's a special little note here. We need to change our percent to a decimal. So even though it's 15%, we're not going to do 1 plus 15 and get 16. What we're going to do is we're going to do 1 plus, but what is 15% as a decimal? Well, remember, you just move your decimal place 2 to the left. So it is here, it's 15.0. We're going to move it 1 and 2. So it's really going to be 0.15. So this is going to be 1 plus 0.15. And then back to our formula, it still says to the power of x. Now, I don't want to write 1 plus 1.15, or I'm sorry, I don't want to write 1 plus 0.15 because I know what that actually is. That's just 1.15. So I'm going to simplify this a little bit. There we go. That looks a little bit nicer. And in fact, if you really like the way that our equations looked before, instead of having these parentheses, you could have a raised dot here. The issue that I have is that now we have a raised dot and a decimal right by each other, and that might start to get confusing if you write anything less than perfectly, like me, as in I don't write perfectly. So let's use those parentheses just so it's not confusing. All right, so now what we're going to do is we're going to figure out how many subscribers they have in 5 years. So this is our part B. So we're going to start with that same formula that we just had. All right, but what are we going to do with this 5 years? Well, we know that X is our number of years, so we're just going to take that 5 and we're going to put it where X is. I don't want to rewrite it, so I'm just going to erase the X and put a 5 there. Now, I'm going to need a calculator to help me solve this. Remember that you have Desmos to do some calculating for you, so let's head over to Desmos. Keep. So our number was 2,750,000. And we were going to do times 1.15 to the power of 5. Oof, a nice big number. Now, remember, we're talking about number of people. So we probably don't want to include the 0.26563. We can round. Since it's a 0.2, let's round down. All right, so we have 5,531,232. Awesome. Okay, let's look at one more example. Let's go back to that snail example from the under course exam. So we're starting with 270,000. And our average rate is 2.9%. Now this time it doesn't say use f of x. It says write an equation that models the population of bats y after x years. Remember, y and f of x are the same thing, so we're just going to have y out front. Y equals, okay, our initial population, 270,000 times, all right, now what is 2.9 as a decimal? Be very careful. I need to go 2 to the left, 1, 2. So it's now going to be here, and you need to fill in this extra space with a 0. So it's 0.029. So if I do 1 plus 0.029, I get 1.029. So that's what number is going to go in here, 1.029. And it's to the power of, it says x. So I'm going to use x. All right, so we don't have any more examples, but I want to talk about all of the situations where you would use exponential functions. So we've seen a lot, magazine subscribers, whatever. Population growth is huge anytime you're talking about population growth, compound interest, like credit card debt. And then the other big thing, which is what we're going to focus on a little bit, is the spread of a disease. So, for example, we could analyze the spread of the coronavirus. And it turns out that we could model that with an exponential function as well. That's exactly what we're going to do next.